Okay, thank you everyone, and welcome to College Algebra. Today we will be discussing section 3.6, which talks about polynomial and rational inequalities. So we would begin with the definition of a polynomial. So definition, write it properly. Definition of polynomial inequality. All right, so a polynomial inequality is any inequality of the form that can be put into one of these forms. So any inequality that can be put into one of the forms. F of x less than 0, f of x greater than 0, f of x less than or equal to 0, or f of x greater than or equal to 0, where f of x is the polynomial, where f of x is the polynomial function. So in a polynomial function that basically involves an inequality sign, whether less than, greater than, less than or equal to, or greater than or equal to, it's a polynomial inequality. All right, so let's look at the steps that we have to take in order to solve a polynomial inequality. So procedure for solving polynomial inequalities. All right, so the first step is we have to express the polynomial inequality of the form where all the terms are on one side and 0 is on the other side. So the first thing is we have to express the inequality in the form f of x is less than 0, or f of x is greater than 0. And the next thing is we have to solve the equation f of x is equal to 0. We have to set the equation equal to 0, like ignore the inequality sign or make the inequality sign to be 0 and solve for f of x. F of x is equal to 0. And the real solutions are boundary points. Boundary points And the next thing is we have to locate the boundary points on the number line. Locate the boundary points on the number line and pick a test value. Locate the boundary points on the number line, pick test values. Pick test values within an interval of the boundary points, within an interval of the boundary points. So we pick test points within the boundary of the interval of the test points. And after picking these boundary points, the next thing is we will evaluate f of x. Evaluate f of x with the test values. Evaluate f of x with the test values. If the value of f, if the value of f is positive, then f of x is greater than 0. Is greater than 0 for all numbers in the interval. If the value of f is negative, then f of x is less than 0 for all numbers in the for all numbers in the interval. All right, and the last one is we'll write a solution set after testing using these test values and finding out whether f of x is greater than 0 or less than 0. We will write the solution set. Write the solution set. Selecting the interval or intervals that satisfy the given inequality. All right, so all these steps will become clearer as we use an example. So let's pick an example. So this is example 1. So example 1 says solve and graph the solution set. Solve and graph the solution set So when I grab the solution set, x squared minus x is greater than 2. X squared minus x is greater than 2. All right, so the first step is we write this inequality such that we have all the terms on the left and 0 on the right. So we write this as x squared. If we subtract 2 on both sides, we have x squared minus x minus 2 is greater than 0. And next, we set this equal to 0. X squared minus x minus 2 equal to 0. Then we solve for the values of x. So if we factorize, excuse me, oh, this was 20. So this is 20, 20, and 20. So the next thing is we have to factorize this inequality, x squared. We have to factorize this equation, x squared minus x minus 20. And we can factorize this. We can rewrite this as x squared minus 5x plus 4x minus 20 equal to 0. And we can factorize x out of this. So x out here, x minus 5. We can factor 4 out of this. So 4 here, x minus 5 equal to 0. And we can factorize x minus 5 out. So x minus 5 times x plus 4 equal to 0. So this means x minus 5 is equal to 0, which means x is equal to 5, or x plus 4 equal to 0, which means x is equal to negative 4. So we have boundary points. So this will be our boundary points. So this will be our boundary points. So the next step is we are going to put these numbers on the number line and pick test points. So we have a number line and our test points are negative. So this is 0, 1, 2, 3, 4, 5, and 6. This is negative 1, negative 2. This is negative 3, negative 4, negative 5. This is negative 6. Okay. All right. So here, so our boundary points are negative 4 and positive 5. So what we do is we pick test values in this interval, test values from test values after negative 4, test values between negative 4 and positive 5, and also a test value after 5, right? So we can create a table, kind of a table, and pick the test point. So we can create a little table we are going to use to evaluate. So let's say this is our interval that we are picking from. This is our test value. This is substitute into f of x. And after we evaluate the test value, we'll write our conclusion here. So our first interval is beyond negative 4 to negative infinity. So negative infinity to negative 4, right? And so we can pick a point here such as -5. So beyond negative, a point after -4 in the interval -infinity to -4, we can pick a number such as -5 as our test value. So -5 here as our test value. And f of x, we know f of x is equal to x squared minus x minus 20. So we will evaluate f of -5. So f of -5 is equal to -5 squared minus -5. Let me write this properly. Minus -5 squared minus x. So minus x is -5 and minus 20. So if we evaluate this, this becomes 25 plus 5 minus 20. So this becomes 10, which is positive. So it means f of x is greater than 0 for all x in this interval. For all x in the interval minus infinity to -4. Right? F of x is positive in the interval minus infinity to -4. And you can tell that our original inequality was greater than, we rewrote our original inequality to be greater than 0. So that means our original inequality is true in this domain. Our original inequality is true in this domain. Let's pick another test point between -4 and +5. So a test point, we are looking at the interval -4 to +5. And we can pick a test value such as 0, and so we will find f of 0. So f of 0 is equal to 0 squared minus 0 minus 20. And this equals to -20. And so we are having a negative number here. So this is negative. And so that means f of x, that means f of x, our original equality said f of x is greater than 0. So f of x greater than 0 for all x in this interval is false. For all x in -4 to 5, -4 to 5 is false. Because f of x is actually, f of x is less than, f of x is less than 0 here. F of 0 is a negative number, so that is less than 0. So we are not getting f of x to be greater than 0. So the statement of f of x greater than 0 is false in this interval. So that means this interval will not be part of our solution because our inequality is false in this interval. And the last interval is also after 5. So 5 to +infinity. So 5 to +infinity, we can pick a number like 6. So we evaluate f of 6, which is equal to 6 squared minus 6 minus 20. And this equals to 10. And so this is positive. So that means f of x is greater than 0. for all x, for all x in this interval 5 to infinity is true. Okay, f of x is greater than 0 for all x in this interval is true, because we pick a number like 6 and it gave us a positive number. So f of x greater than 0 is true in this interval. So the last thing is now we have to write our solution set. So we can tell that for our solution set, we can say that this, since f of x is greater than 0 is true in this interval, this will be part of our solution set. This will not be part of our solution set because we got a false statement there, and this will also be part of our solution set. So let's write down our solution set. So as our solution set, we know that f of x is greater than 0 for all x in minus infinity to -4 and +5 to infinity. So the solution sets would be the solution sets for f of x for the inequality x squared minus x greater than 20 is minus infinity to -4 union 5 to positive infinity. So this will be our solution set. Okay. So the next thing is let's look at rational inequalities. So let's first look at the definition of a rational inequality. Let's look at the definition of a rational inequality. Okay, so a rational inequality is any inequality that can be put into one of the forms um, f of x greater than 0, less than 0, where f is a rational function, such as so a rational inequality is any inequality that can be put into one of the forms f of x less than 0, f of x greater than 0, f of x less than or equal to 0, or f of x greater than or equal to 0, where f is a rational function. Where f is a rational function. All right, so let's use an example to illustrate what a rational function inequality is. So this will be our second example. So this will be our example 2. And it says solve this inequality. Solve and find the solution set. So we're going to find the solution set 2x divided by x plus 1 is greater than or equal to 1. So this is a rational expression because we have we have a term at the numerator and another term at the denominator. So this is what we mean by a rational function. All right. So to solve this rational function, like as usual, we will write it as 2x divided by x plus 1, subtract 1 on both sides, so minus 1, and this is greater than or equal to 0. And so from here, we can multiply through by the LCM, and that will give us 2x divided by x. We can we can we can write this all to have the same denominator. So that will be 2x plus x plus 1 minus 1 times x plus 1 divided by x plus 1, which is the same thing. X plus 1 divided by x plus 1 is still 1. So this is greater than or equal to 0. And so they all have the same denominator now. So we have x plus 1 and 2x minus x, we multiply through by negative 1. So negative x minus 1. And this is greater than or equal to 0. So this gives us 2x minus x is x. And we get x minus 1 divided by x plus 1 is greater than or equal to 0. Um, and so we can say that this form that we have, x minus 1 divided by x plus 1 greater than or equal to 0, is equivalent. This is equivalent to the original form, which was 2x divided by x plus 1 greater than or equal to 1. So these two are equivalent because we didn't really do anything. All we did was to simplify the original form to x minus 1 divided by x plus 1. All right, so the next point here is to pick test points. So if we are solving this inequality, we will set the denominator equal to 0, and we will set also the numerator equal to 0 and solve for the boundary points. So for the boundary points, we will have we will set the denominator of we set the denominator here to 0 and also the numerator to 0 to find the boundary values from which we will put on the number line to determine the test point. So the numerator x minus 1 is equal to 0 implies x is equal to 1 is a boundary point, and x plus 1 equal to 0 implies x is equal to negative 1 is a boundary point. So these are our boundary points. All right, so the next is we put these on a number line to pick our test points. So this is 0, this is 1, 2, 3, and this is negative 1, negative 2, negative 3. I think I forgot to do one thing in the previous problem, which is to graph the solution set on the number line. So let's try to do that. So yeah, in the previous example, so we found out that the solution is, the solution is this. We should have graphed it on the number line. Okay, so the solution is from -4 to negative infinity. Um, the the function is defined on this range. So on the number line, let's go back to our number line. So on the number line, we will have the function goes from -4 to positive infinity. It's true. And the function also goes from +5 to infinity. And we are using this sign because there is an open, we have this open parenthesis here. So that's why we're using this open parenthesis. And we have this open parenthesis here. So here we use the sign open on the number line. So this is how we graph the solution on the number line. All right, so let's go back to current example. So our current example, let's go back to it. All right, so these are our boundary points. So we're going to pick test points. So we can pick a test point between -1 and +1, such as 0. You can pick a test point between -1 and +1, such as 0. You can pick a test point after 1, such as 2. And we can pick a test point also after -1, such as -2. So this will be our test points. So let's put them on a table. So let me do that on the next page. So we have our interval. We have our test value. We have our test value. And we have f of x, which is equal to x minus 1 divided by x plus 1. And we have our conclusion here. Okay, so from -infinity to -1, our test point is -2. So we find f of -2. Which is equal to f of -2 is equal to -2 minus -2 minus 1 divided by -2 plus 1. So this is equal to -3 divided by -1, which is +3. So we have a positive here. So f of x evaluates to a positive value here. So our original inequality f of x greater than 0. So here f of x is greater than 0 for all x between negative infinity to -1. And this statement is true. This statement is true. And the next test point is -1. The next test interval is -1 to +1. So we pick a test point of 0. we get test point of 0. So f of 0 is equal to 0. F of 0 is equal to 0. 0 minus 1 divided by 0 plus 1, which is negative 1 divided by 1, which is negative 1. So we get a negative here. We get a negative here. So our original inequality, since we are getting a negative, f of x is not greater than 0. So the statements of f of x are greater than or equal to 0 for all x in this interval -1 to +1 is false. So this statement is false. So we can't, it's false because we found that f of 0 is a negative number. So this statement is false. All right, so then the last interval is 1 to infinity. And so we pick a test value of 2. So f of 2 is equal to 2 minus 1 divided by 2 plus 1. And this equals to 1/3, which is positive. Which is positive. Okay, so f of x is greater than or equal to 0 in the interval for all x. For all x in 1 to infinity is true. It's true. So we can see that again, this is true. So this will be part of our solution set. So this will be part of our solution set. This will not be part of our solution set because f of x is false in that interval, and this will also be part of our solution set. So our solution set would be, so the solution set would be, our solution set will be minus infinity to positive, minus infinity to -1, and this union 1 to positive infinity. And we have a closed set here because of the greater than or equal to in the inequality. Or we can also rewrite this equivalently as x is said that x is less than -1 or x is greater than or equal to +1. All right, so let's graph this on the number line. So on the number line, we will have x goes from here, open set goes from here all the way to negative infinity, and x goes from here, which is a closed set, from here to positive infinity. So this is how we visualize this on the number line. All right, so let's look at some application question. Let's look at another example that involves some sort of an application. So let's look at this example. So this should be our example 3. And it says an object is an object that is falling, or vertically projected. An object that is falling or vertically projected into the air has a height into the air has its height above the ground, st in feet given by st is equal to negative 16t squared plus v0 of v0 times t plus so where v0 is the original velocity, original or initial velocity, which is the same thing. The original velocity of the object in feet per second, and t is this time. T is the time that the object is in motion. And that the object is in motion in seconds, and S0 is the original height, is the original or initial height of the object in feet. Okay. Um, okay, so you know what? Let me rather change this. Let me see. Let me vary the question slightly. Um, Let me vary the question slightly. So um, instead of V0, let me change the question slightly. Let me change the question slightly here instead of uh, okay, or let me say V0, V0, okay. All right, so this is let me add this to the question that V0, the initial velocity, V0 is equal to 80, is equal to 80 um, feet per second, is equal to 80 feet per second. And initial height, the initial height, the initial height is 0. Let's make the initial height to be 0. The initial height is 0. The initial height is 0 is also equal to 0. Okay, so that means our function st becomes negative 16 t squared plus 80 t negative 16 t squared plus 80 t 80, and s of 0 is 0. So this becomes our distance. This becomes the function that models um, the distance traveled by the object at any time t. Um, all right, so um, um, distance by the travel by the object at any time t. All right, so the question is, in what time? So the continuation of the question is, in what time? In what time? Um, in what time interval the object will the object be more than 64 feet above the ground? Okay. Uh-huh. Okay. So we have our distance function st is equal to negative 16t squared plus 80t. And we want to find the time at which the distance is 64 above the feet. So that means I want to find the distance, we want to find the time at which negative 16t squared plus 80t is greater than 64, right? So we can write this as usual, all the terms on one side, so negative 16t squared plus 80t, and subtract 64 on both sides, minus 64 is greater than 0. Okay. And we can set this equal to 0 and solve for t. So you can see here that we have 16t squared 80t minus 64. So for this, first of all, we can factor out 16 from this term. So we can factor out negative 16. So if we factor out negative 16, so first of all, let me set it to equal to 0. So 16t squared plus 80t minus 64 is equal to 0. And so we factor out negative 16. So negative 16 times t squared. We can factor negative 16 out. So if we factor negative 16 out, we have t squared here. And we factor 16 out, negative 16 out of 80, we'll have a negative 5t here. And we factor negative 16 out of 64, we have a positive 4 here. And this equal to 0. And so if we divide both sides by negative 16, so we have t squared minus 5t plus 4 equal to 0. Okay, so with this, we can factorize and solve for t. So we have, this is the same thing as t squared minus 4t minus t plus 4 equal to 0. So this would become, if we factor t out of the first two times, t times t minus 4, and if we factor negative 1 out of the third and fourth, minus 1 t minus 4. So we have t minus 4 times t minus 1. So our boundary points are t equals to 4 and t equals to 1. So this will be our boundary points. So let's put this on a number line. So we have a number line. So this is 0, 1, 2, 3, 4, 5, 6. This negative 1, negative 2, negative 3. All right, so our test points are 1. Our boundary points are 1. Boundary points are 1 and 4. So we'll pick values after 4. In this interval, we'll pick values after 4, and we can pick something like 5 as our test point. Between 1 to 4, between 1 to 4, we can pick a value like 2. So between 1 to 4, we can pick a value like 2. We could have also picked 3 or any other number between 1 and 4. And after below 1, we can pick a number like 0. And so since this is time, it only comes up to this point, right? So between 0 and 1, we can pick a value like 0.5. Since this is time, it doesn't, we don't go to the negative region. It's only up to it's only that t is time, so it's only up to 0. It doesn't go below 0. Also, let me modify the number line to make it clearer. So t goes only up to 0. Okay, so let's evaluate, let's use our test points to evaluate our function. So our interval is, we have our interval here, and we have our test value. Of our test value, we have our substitute into f of s. F of x is, let me write down the f of x here rather. Our s of t is negative 16 t squared minus 80 plus 80t minus 64. And our conclusion is here. And our conclusion will be here. All right, so we have 0, 1. In the interval 0, 1, our test point is 0.5. And so we substitute 0.5 into s of t. So that will be minus 16 times 0.5 squared plus 80 times 0.5 minus 64. And we evaluate this, and this equals to negative, on our calculator, this equals to negative 28. So we get a negative here. So that means s of t s of t greater than 0 for all t in this interval is false. For all t in 0, 1 is false. S of t is not greater than 0 here. So s of t is less than 0. So the statement s of t greater than 0 for all t in this interval is false. And our next interval is 1, 4, and we pick a test value of 2. So we evaluate minus 16 times 2 squared plus 80 times 2 minus 64. And this equals to 32. So we get a positive here. So the statement s of t greater than 0 for all t in 1, 4 is true. This is true. And so the last interval is 4 and infinity. So 4 and infinity, we can pick a test point of 5. So we have minus 16 times 5 squared plus 80 times 5 plus 80 times 5 minus 64, and this equals to negative 64, which is negative. So the statement S of t greater than 0 for all t in 4 to infinity is false. So this statement is false. So that means our solution set will be made up of only 0 and 1, because here this no, between 1 and 4 rather. So here the statement is false here. The statement is false here, so this will not be part of our solution. The statement is true here, and the statement is also false here, so this will also not be part of our solution. So that means on the number line, S of t, the solution set will be made up of value between only 0. S of t is only true for values between 1 and 4. So the solution set would be x is between the solution set. So for the solution set, let's test the boundary points. If let's test the boundary points. So the solution set is only true for between 1 and 4. So S of 1, if it's 1, so if it's 1, it's true. So 1 will be true. Let me see what I'm saying. So S of 1, let me test S of 1. S of 1 will be equal to minus 16 plus 80 minus 64. So this should be equal to 0. All right, so S of t is equal, so it's not really greater than, but we want a really greater than. So let me test for S of 4. S of 4 will also be, let's see, will it be positive or, let's test S of 4. So S of 4 will be negative 16 times 4 squared minus plus 80 times 4 minus 64. So what would that give us? Let's evaluate this on our calculator. So minus 16 times 4 squared, which is also 16, and plus 80. Yeah. So we have minus 16 times minus 16 plus 80 times 4. Plus 80 times 4. Eighty times 4 minus 64. So that also gives us a 0. That also gives us a 0. So the solution set will be between t is between 1 and 4. So the solution set would be between 1 and 4, or t is said that 1 is less than t, which is less than 4. This will be our solution set for this example. Okay, so let's look at one more example, one last example, which is also of a rational function. So this will be our example 4. So example 4. So example 4, it says, solve and graph the inequality. Inequality set on a real number line. On a real number line, and express the solutions, express the solution sets. Solution set in an interval notation. Okay, so we have 3 divided by, our rational expression is 3 divided by x plus 1 is greater than 3 divided by x minus 2. So the first thing, we write every term on the left. So 3 divided by x plus 1 minus 3 divided by x minus 2 is greater than 0. And so the LCM here is x plus 1 times x minus 2. So if we multiply through by the LCM, we have 3x plus 1 times x plus 1 x minus 2 minus 3 divided by x minus 2 times x plus 1 times x minus 2, and this equal to 0. And so x plus 1 cancels out, x plus 1, x minus 1 minus 2 divides x minus 2. So we have 3x minus 2 minus 3 x plus 1 is equal to, let me keep the inequality sign here. This is greater than 0. So we have multiplied through by 3. 3 times x is 3x. 3 times negative 2 is negative 6. Minus 3 times x is 3x. Negative 3 times negative 1 is negative 3. And this is greater than 0. So 3x subtracts from 3x. So we have negative 9 greater than 0, which is a false statement. So our test points will be the values at the denominator. So our test points in this example here will be obtained by setting the denominator equal to 0. So x plus 1 equal to 0 means x is equal to -1 will be a boundary value, and x minus 2 equal to 0 means x is equal to 2 will also be a boundary value. So on the number line we have boundary values of 1, -1, and 2. So we have a 0 here. The boundary values are -1 and positive. Boundary values are -1 and +2. So we pick values in this interval. So from 2 to infinity, we'll pick a value. So our intervals are here is 2 to infinity. And we can pick a value such as 3. And we also have -1 to -2. -1 to +2. We can pick a value such as 0 as our test value. And also from -infinity to -1, we can pick a test value such as -2 here. So let's obtain our interval. Let's write up our interval, our test value. Our test value, and our f of x is equal to 3 divided by x plus 1 minus 3 divided by x minus 2. We can have our conclusion here. Okay, so minus infinity to -1. The minus infinity to -1, our test value is -2. So f of -2 here would be 3 divided by -2 plus 1 minus -3 divided by -2 minus 2. So this will be equal to 3 divided by -1 minus 3 divided by -4, which gives us -9 divided by 4, which is negative. So the statement f of x greater than 0 for all x in this interval, -1, -infinity to -1 is false. This is false because f of x is actually less than 0. And so the interval, let's look at the interval -1 to 2. Let's pick 0. So f of 0 is equal to 3 divided by 0 plus 1 minus 3 divided by 0 minus 2. And this gives us 3 plus 3 divided by 2. So this gives us 3 plus 3 divided by 2, which is 9 divided by 2. So this is positive. So that means f of x greater than 0 for all x in the interval -1 to 2 is true. Is true. And the last interval is 2 infinity, and this is 3. So f of 3 is equal to 3 divided by 3 plus 1 minus 3 divided by 3 minus 2. So this is equal to 3/4 minus 3, which is -9 divided by 4. So we have a negative here. So this is negative. All right, so the statement f of x is greater than 0 for all x in 2 to infinity is false. Is false. So that means f of x, that means this interval will not be part of our solution. This will be part of our solution, and this interval will also not be part of our solution set. Okay, so on the number line, we will have f of x only lies between this interval -1 and 2. So our solution set will be f of x is between 1 and 2. So let's write that down. So our solution set will be equal to -1 and 2. Or x is said that -1 is less than x, and x is less than 2. So this should be our solution set. All right, so this brings us to the end of our lesson for today, and we will begin the next section soon. See you in the next video. Bye-bye.